Right, so I'm looking at bottom up together with Russ Lavery, who is at the back there. But I'm going to start with an interesting question. And since we don't do a lot of talking, you need to find a partner and answer that question to say, if you look at doing voltage optimization, which is quite a buzzword at the moment in various energy sectors, and you get it so that you start off at 240 volts, you put your magic piece of equipment in and you reduce to 220, roughly how much energy do you think you'll save when you boil a kettle of water? Talk to the person next to you, or around from you, and you've got about 30 seconds. Okay, so we've got about a 10% change in voltage, and the answer is, we'll find out later. So we've said, Katie mentioned that this is a wicked problem, and I'm an engineer, so I try and simplify things down a bit, and I find, technology is pretty complex, people are even more complex, so when you work in the energy space, it's quite difficult. So I try and get a simple model in my mind, which gets me to ask the right sort of questions. And this is an energy cultures framework, which comes sort of imported from New Zealand, which I find very, very powerful, and basically says, when you're trying to understand what's happening within the energy behavior and usage within a particular context, it's worthwhile asking three different questions. The first question is to say, what are the norms and the aspirations and traditions of the people that are actually making the decisions and actually behaving in it? And that's quite a useful place to start. The second one is to say, what are the material assets they have that, to play with? So in this case, it could be things like, what are the buildings that you have, but also what are the loads that are within those buildings. And the third one is to say, how do we look at behavior? How do people actually use that stuff and play with it? And you basically broadly two types of categories of behavior. One is infrequent behavior, which is things like maintenance regimes, or you're doing a complete refit out, or you're doing those infrequent but large changes. And then there's the much smaller repetitive behaviors like turning the lights on, when do the fridges kick in, that type of thing. So what I want to do at the moment is just give a little insight into say how I want to tackle. We want to look at both material assets and buildings, because we want to try and understand that interrelationship, and to say how do those material assets and energy behavior interact with each other. And we also want to try and understand to say that how do the norms and aspirations people have, how do they actually translate into behavior as well. So, I'm going to give you an example where we're looking particularly at the loads and repetitive behavior, but we want to look at the other four interactions as well, so buildings and infrequent and frequent behavior, and we're working with the middle out because that kind of deals with that one quite a lot. Okay, so in order to do that, one of the things we want to look at is what data do we need to try and understand behavior. And this is some work that we've been doing for various other projects, but it's quite a useful one, which basically says, down the bottom here is to say, does this actually give us, well, this is giving, you can only go forward, right? I thought it had a laser pointer, does it have a laser? Ah, it does, but it's underneath. Okay, so this is basically saying how fast do you take the data? Okay, so how often are you taking the data? This is how long are you interested in keeping the data for? So, John will know, if you're looking at grid protection, you want to work reasonably fast, but you don't want to know about it for a very long time. You just want to act and deal with it. If you're looking at your kind of space, is that there's energy management and smart meters. If you see the amount of information flows is pretty slow, but we want to keep it for a pretty long time, multiple years of time. And as you start to move into the space, so you need more and more memory as you're going along. And one of the problems that you have is that if you're starting from here and you've got data in this area, you cannot move to the right. But if you're on the right, you can move to the left. Okay, you can always go down, but you can never go up. So one of the questions is to say, where do we need to be working in that space to understand behavior? So to give an example from the domestic sphere, because it's one that I've got a lot of rich data from, but I've also got some in non-domestic, but I'll take this one here, is to say, let's have a look at a typical household. This is on GMT and it's on BST, so there's an hour difference there. But this is typical half-hourly data that you would see, that you all, in energy management, you love and know well. The axis, instead of using kilowatt hours, I'm actually using average power because I'm changing the time scale as we move along. So I'm using power just to keep it so the units stay the same. And if you see that the peak is something just after 5 o'clock, we'll add an hour on just to normalize it. And the peak is something around about 4.2 kilowatts, and it's a classic morning and evening energy curve that you see. However, this is looking at that hour, that data averaged over a 30-minute interval. If we take the same data and we average over a 5 minute data interval, what you find our peak is no longer 4.2, but 5.8. Okay? And also we can see it's a lot more peaky and there's a lot more going on. If we now go down to a 1 second data point, we find the peak is actually 8.2 kilowatts, but not at the time we thought it was. It was actually more like 9 o'clock in the morning. Okay? So what you're saying is that the rate that you sample the data at is actually critical if you really want to try and dig in and get underneath the data to understand what's going on. What I'm going to do is to say, if we zoom in this section in the morning here, okay, so if we just zoom, the next slide is going to zoom in there. What's quite nice is that we can take this high level data and we can start to understand what's going on. So if you see here, we've got something that's going on for about 2 kilowatts for a fairly short time period. If you know your oats, that's actually a hot water tank, and we'll see that it repeats itself. So it's there. So those are all hot water tank events. The next one we can see coming along, that spike with the low one is a classic of a fridge. So where we see a spike coming along, there's another fridge event there. Those are all fridge events. Then we can go along, we can see there's a heater that's turned on because again it's about 2 kilowatts, but it's on for a very long time. Those are classic electric hob type of events. And there's a kettle. So what we can say is that when you start to actually look at a much tighter time resolution, you can now tie data back to behavior. And that's one of the things we want to now do in the retail space, is to say, actually, if we're taking really high frequency data and really detailed one, can we actually infer what the behavior of the different appliances are going on? Now, we've had a whole research group going for quite a while now, where we're looking a little more than just the time sequences, but looking at the harmonics of the data, and we're going to infer what type of appliance is turning on and how much energy is consumed by those. So what we find is that actually, in order to look at behavior properly, we need to be operating in that sort of space in our diagram. So we'd be looking, we need to be sampling at about 10 to the 4 bits per second. So it's like around about, that works out something like a tenth of a second or something like that. And in our team, we actually have capability to go right up to 10 kilohertz of sampling per second. I've now got data on a house which is sampled at 10 kilohertz. It's 3-phase data that's going into the house, and we stored it for 2 years. So we could, it's about 6 terabytes worth of data. But we're busy processing that, and so part of our team is doing to say, in a vast amount of data, what are the actually really interesting bits? Because a lot of it is just the same old thing carrying on for a lot of time. We want to understand what the really interesting bits is. So what we're saying is that if we can get hold of that data, we can then start to really dig down and understand what's going in the behavior of the system, and so that we can then start to say, how does that play with our assets, with our norms and aspirations? So, coming back to our interesting question. Quick answer, how many of you said 5% decrease in energy? 10% decrease in energy? More than 10%? Stays the same? Gets worse? Okay, so the answer is it's about 20% less power. So more than 10%, but that's power or energy. And so you've got to be careful. It actually uses 5% more energy because it takes longer to heat up, so the losses are worse, so you actually use more energy. So something that is sold as an energy efficiency device, in some context, actually makes things a hell of a lot worse. So you've got to know what's going on. You need to understand what your loads are doing, what proportion of your loads are actually dependent on voltage and how they're dependent on that, and then you can make a correct strategic decision, because you could be spending lots of money on something that's supposedly energy efficient and actually makes life worse for you. Thank you.